This video we're going to be talking about applied optimization. The problem I used was we want to build a box whose base is a square and has no top and will enclose 100 meters cubed. Determine the dimensions of the box that will minimize the amount of material needed to construct a box. So for volume, you use length times width times height. So for the constraint, volume would equal x squared, 2 of x's, times y, equals the amount we're trying to get, which is 100 meters cubed. So to find the total amount of surface area, we have to find the area of all the 4 faces. So that equation would be x squared plus 4xy, because each surface has x as a base and y as the height. Next, we'll want to find y within the constraint and then plug it into the surface area equation. So here's the constraint. To find y, we just divide each side by x squared. And then you'd get y equals 100 over x squared. And then when we plug that in to the surface area equation, you get x squared plus 4x times 100 over x squared. After some simplifying, you'd get x squared plus 400x raised to negative 1. And then you would want to find the derivative of that, which would be 2x minus 400x raised to the negative 2 power. And you set that to 0 to find the critical number. And when we set that to 0, you want to get rid of the denominator here to simplify it more. So you times each side by x squared. Get 2x cubed minus 400 equals 0. From there, divide by 2. Get x cubed equals 200. And then you do the radical 3 over this 200. And the critical x value comes out to be 5.84804. So that'd be the value of x on the base. Next, we're going to want to find the value of y. Next, we're going to find the double derivative, the derivative of the first derivative we found. So the first derivative we found was 2x minus 400x raised to negative 2. And when we find the double derivative of that, we would get 2 plus 800x to the negative 3rd power. To simplify that, to have no negatives, it'd be 2 plus 800 over x cubed. Then we would plug the x value we found, the critical number, into this derivative to find whether it concaves up or concaves down. So when we plug this x value into the double derivative, we find out that it's going to be greater than 0, this number. So it'll be concaving up at the value x, 5.84804. To find the value y, which is going to be the last step to find the minimized material needed for this box, we'll have to go back to this equation here, which is y equals 100x squared. We're going to want to plug the x value that we found, which is 5.84804, into that. So here we go is y equals 100 over 5.84804 squared. And that's going to be y equals 2.92401. And so lastly, the dimensions that would minimize material needed for 100 meter cubed box would be 5.84804 meters by 5.84804 meters by 2.92401 meters. And that's the end of this one.